This is the follow-up to the broader AI coding CLI architecture video, but the scope is narrower and more practical. The question here is not what the whole product is. The question is how these agents become repo-aware in a way that feels reliable instead of haunted. Once you start using Codex, CLAUDE Code, or Gemini CLI seriously, that is the next thing you care about. Why did it follow one rule and ignore another? Why did it know the right test command? Why did it ask for approval in one place but not another? The answer is that repo awareness is engineered. It comes from instruction files, reusable task, guidance, tool registration, trust settings, and context assembly. This deck walks through that layer directly. The previous video made a broad argument. Modern AI coding, CLIs converge on the same overall shape. There is a user interface, an orchestrator, a context builder, a tool runtime, approvals, and sometimes subagents. This video zooms in on one layer inside that system. The repo binding layer is where the generic coding agent turns into your coding agent for this codebase. That is where local instructions live, where task-specific procedures are attached, where trusted capabilities show up, and where your workflow rules stop being abstract. It is also the layer that matters if you want to carry this pathway forward into local AI application architecture. It is basically a small control plane attached to a repository. People talk loosely about an agent learning the repo, but that phrasing hides the mechanism. The useful part is not mystical understanding. The useful part is that the tool loads a structured environment before it starts making decisions. It reads durable instructions. It resolves which tools and servers are available. It checks the current trust and approval settings. Then it builds context for the actual task. That means repo awareness is not just a bigger prompt. It is an execution environment made out of files, policy, and state. This is why good repos produce noticeably better agent behavior than messy repos, even with the same model underneath. One hidden reason these tools feel more controllable than generic chat is that they rely on instruction precedence. There is a baseline owned by the product. There are user defaults that express trust and workflow preference. There are repo-local files that say how work should happen here. Then, there may be a task-specific skill, command, or plan step that narrows the guidance further for one moment. This matters because conflicts have to resolve somehow. The good tools expose that reality instead of pretending every instruction lives in one flat space. Once you start thinking in precedence layers, a lot of odd behavior becomes easier to debug. These markdown files matter because they turn the repository itself into a control surface. The terminal view makes that easier to see. A root file defines broad project rules, then a deeper file narrows behavior for the payments subsystem that is much more powerful than one global instruction blob. The guidance stays close to the code it governs. The repo stops being passive input and starts behaving like configuration for the agent. This is also why version control matters so much here. When the instruction surface changes, the behavior surface changes. That is something teams can review, diff, and discuss like any other engineering artifact. The best instruction files read like operations guidance, not culture. The diff view makes the change obvious. A vague file full of values like use your judgment becomes an operational file that names build commands, file boundaries, approval rules, and completion criteria. The model cannot execute vague values. It can execute named commands, explicit rules, and clear boundaries. That is an important lesson both for using these tools and for designing local AI apps more broadly. If you want reliable behavior, write the environment so reliable behavior is the easiest interpretation. Hooks solve a very specific problem. Some behavior should happen because of an event, not because the model happened to remember a paragraph in an instruction file. Formatting after edits, a warning before deploy commands, a reminder when the work tree is dirty, or a notification after a long-running task all fit better as lifecycle hooks than as giant prompt text. Claude Code is explicit about hooks. Other tools expose adjacent mechanisms through commands, scripts, or automation surfaces. The architecture lesson is that not every behavior belongs in the model turn. Some of it belongs in the surrounding runtime reacting to events. Every specialized workflow lives in the root instruction file. The context gets noisy fast. Skills and commands are the answer to that. They let teams attach a heavy, explicit procedure to a name. and load it only when it matters. Codex documents skills directly. Claude Code supports custom commands and related workflow packaging. Gemini CLI exposes commands policy and tool surfaces that fill a similar architectural role. The common pattern is lazy specialization. Durable rules stay small. Detailed task procedures become named modules that makes the agent easier to steer and the repo easier to maintain. With MCP, external systems become named tools behind a consistent interface. That means documentation, search, ticket systems, browser automation, internal developer portals, and company-specific services can all enter the agent loop without every integration feeling bespoke. The repo can suggest what tools are relevant. The runtime can decide which ones are registered. Policy can decide which ones are usable right now. That separation is what keeps the system extensible without turning it into an unreviewable blob of hidden glue. This is a useful distinction because people still talk about tools like they are optional chatbot plugins. In a serious coding CLI, tools are the runtime the model proposes an action. The runtime mediates that action, executes it in the allowed environment, streams the output, and then feeds the result back into the loop. That is why repo-local instructions can be so concrete. They are not telling the model to imagine a workflow. They are telling it how to operate a real runtime attached to a real repository. Once you see that MCP approvals, hooks, and repo instructions all line up as parts of one execution system. These concepts get blended together constantly, but they should not. Trusted folder state is not the same thing as approval mode. Approval mode is not the same thing as sandboxing. Policy is not the same thing as any of those. Policy sets the envelope. Approval decides when a human stays in the loop. Sandboxing defines blast radius. That separation is what lets a repo feel productive without feeling reckless. For example, a tool can be trusted enough to read and patch workspace files while still requiring approval for network access or dangerous shell commands. If you collapse those layers into one yes or no switch, the workflow becomes either annoying or unsafe. This is one of the most important distinctions in the whole deck. Repo files are durable guidance. Context assembly is a per-task build step. They solve different problems. Durable instructions say how work should happen here. Context assembly says which files, diffs, summaries, and tool outputs belong in the next model turn right now. If a system mixes those responsibilities together, the agent becomes harder to reason about. Good tools keep them separate so they can summarize sessions, compact transcripts, state, checkpoint work, and refresh relevant files without losing the durable rules of the repo itself. Another common mistake is to treat everything persistent as one category. It is not. Repo rules persist because they belong to the codebase. Planned state persists because the task is not done yet. Session summaries persist because a transcript would get too large. Checkpoints persist because recoverability matters. These are different storage problems and they belong to different layers of the architecture. That distinction becomes even more important when you move from coding CLI workflows into more general local AI applications. The same system usually needs durable product rules, task state, and resumable execution all at once. If you want better agent behavior, design a better repo. That sounds obvious, but it is the core lesson. Explicit verification commands, stable file formats, architecture notes, and diffable configuration make the environment legible. Hidden state, magical side effects, and inconsistent workflows make the environment hostile. This is why serious local AI application design keeps pushing toward text artifacts, deterministic tools, and explicit approval boundaries. A coding agent simply exposes that requirement faster. It tries to operate the environment continuously instead of waiting for a human to bridge every gap by hand. When users say the agent feels random, they are often describing a repo or runtime design problem rather than a model problem. Vague rules force vague interpretation. Tool overload creates indecision. Hidden GUI state leaves the runtime blind. Unclear hooks make the workflow feel haunted. Something changed and no one understands why. The fix is usually not more model power. The fix is clearer control surfaces, better instructions, better tool naming, better policy separation, better artifact design. In other words, the path to reliable agents looks a lot like ordinary software architecture discipline. This is the mental model I would keep after the video. The user talks to a CLI, but the real system is an orchestrator that loads instructions, assembles context, applies policy, and routes tool calls. The repository participates through instruction files, scripts, and local artifacts. MCP expands the capability surface. The model sits inside that loop rather than above it. This is also the bridge to your broader architecture interest. Once a coding CLI already has instruction loading, context assembly, tool mediation, and policy, it has most of the same control plane patterns a broader local AI application needs. If the first video answered what AI coding CLIs are, this one answers how they bind themselves to one real code base. The answer is not one giant prompt. It is a layered system of instructions, tools, policies, and state. That is why this topic is worth expanding. It is useful for people trying to use Codex, Claude Code, Gemini CLI well today. And it is also useful for people who want to build the next layer of local AI software themselves.